Okay, today we'll discuss about session 38. In the 38, we'll discuss about Andrews experiment on carbon dioxide. So here we understood what is meant by real gases, how the real gases behavior will be there by using Andrews experiment of real gases. Now, in the Andrews experiment have been done like this H-shaped tube they have taken, and the two tubes have been taken, and first we have filled the gas in one, another one air we have filled, another one is carbon dioxide filled, and the mercury has been inserted, and the plunger screws are being placed, and these are maintained at the same temperature. Air and carbon dioxide is maintained at the same temperature as shown in the diagram. Now, when we made this temperature, the temperature of air and carbon dioxide are fixed at constant value. After the operators are set up, the plunger screws are tightened till the mercury level rises above the steel tubes. The volume of the air and the carbon dioxide is measured in the graduated capillary tubes. The pressure is calculated by using a Boyle's law to air. Maintaining the same temperature of carbon dioxide and volume of the gas is measured at different pressures. The process is repeated for different temperatures. Andrew did the experiment at the following temperature, that is at 13.1 degrees Celsius and 21.5 degrees Celsius and 31.1 degrees Celsius, 32.5 and 35.5 and 48.1. So, on these temperatures, Andrew got a graph like this as shown in the figure. See, at first curve ABCD is called as 13.1, and EFGH you got 21.5, and another one is 13.1, next one is 32.5 and 35.5 and 48.5. These are the isotherms got for an Andrews for the gas called as carbon dioxide like this. And in this graph, we interpret the readings for this. See, at 13.1 degrees Celsius, the portion AB are called as gaseous phase of carbon dioxide. As the pressure increases, volume is decreases up to a point B. So here the Boyle's law is obeying perfectly. From B to C, volume suddenly decreases enormously at constant pressure. This means that gas is condensing at a constant pressure. The portion BC represents the changing the phase of carbon dioxide from gaseous to liquid state. In this state, vapor and liquid coexist and are in the equilibrium. Up to C. At C, the gas is fully liquefied, and any further increase in pressure practically does not alter the volume. CD represents the liquid state of carbon dioxide. This is the first interpretation of a curve at 13.1 degrees Celsius. And at 21.5 degrees Celsius, the curve is similar and the behavior of carbon dioxide is similar to the lower temperature of 13.1, and only that original horizontal portion of FG is shorter than the BC. This means that liquid and vapor state coexist of a short range. As can be noticed that volume at that time the condensed state is lesser and its volume at 13.1 degrees Celsius. But the volume of a liquid can condense longer. Note the particular that pressure required to liquefy is larger. Then the third interpretation is that at temperature 13.1 degrees Celsius, the original portion of isotherm has been removed by a clink. This isotherm is called as critical isotherm, and this is the significance. The corresponding temperature is called as critical temperature. The clink or the point of inflection at a point I suggests that gas can be liquefied with the application of large pressure. Above this temperature for 35.5 and 48.1, we see that the horizontal portion of isotherm has completely vanished. This means that the gas cannot be liquefied whatever be the pressure applied on the gas. Further, we notice that the curve is similar to an ideal gas. In fact, the gas is obeying Boyle's law in this region. This region represents gaseous phase of carbon dioxide. Thus, we conclude that critical isotherms divides the graph into two regions. Above the critical temperature, that is 31.1 degrees Celsius for carbon dioxide, cannot be liquefied, however the high pressure may be. while the below the critical temperature of carbon dioxide can be liquefied by applying the pressure. The point of inflection is called as critical point. So, from these interpretations, Andrews concluded that for every gas has a maximum temperature called as critical temperature, above which cannot be liquefied by applying application of pressure. The second one is every gas is a set of constants called as critical constants associated with critical constants. Then critical constants means critical pressure or critical temperature and critical volume. What is critical temperature? The maximum temperature at which gas can be liquefied by applying the pressure alone. Critical pressure means the pressure necessary to liquefy the gas at critical temperature. Critical volume means the volume occupied by unit mass of a gas at its critical temperature and critical pressure. Then critical molar volume is the volume occupied by a mole by a gas at its critical temperature and critical pressure is known as critical constants of a gas. Critical point means the point at a critical isotherm of a gas at which change of state from gaseous to liquid phase takes place at constant values of Pc and Vc. Now, like gases like oxygen, nitrogen, hydrogen, critical temperatures are of minus 118.6 degrees Celsius, minus 146.9 degrees Celsius, and minus 239.7 degrees Celsius respectively. Hence, these gases cannot be liquefied at room temperature. They were referred as permanent gases until the technology to cool these gases to their critical temperature we developed. Hence, Andrews concluded that gases and liquid phases only are the distinct stages in the long range of continuous physical changes that a substance can undergo. The most important result evidence that the fact that higher the temperature of a gas for a critical temperature, the more closely behaves like a ideal gas. So in this session we concluded that we learned Andrews' experiment on carbon dioxide and we learned how this carbon dioxide behaves at different temperatures by varying the pressure and volume. Now we'll see some of the questions. In high pressure condition, real gases conforms more close to the van der Waals equation, ideal gas equation, both A and B, none of this. So we know that it is ideal gas van der Waals equation. Which is the state of substance for which the phase change occurs without any change in pressure or volume? So it is pure state, phase state, saturated state. So it is saturated state. The volume of 2.8 grams of carbon monoxide at 27 degrees Celsius and 0.821 atmosphere R is equal to 0.0821 liter per atmosphere mole per gram. So if we calculate the gram volume is, we'll get 3 liters. According to kinetic theory of gases, at absolute temperature, water freezes, liquid helium freezes, molecules motion stops, liquid nitrogen freezes. So it is molecular motion stops. 1 mole of ideal gas requires 207 joules heat to rise the temperature of by 10 Kelvin when the heat at constant pressure. If a same gas is heated at constant volume to rise the temperature of 10 Kelvin, then the heat is required 124 joules. So these are the some questions on this topic. To refer this topic, these are the books you can refer for the further